Today we're going to be working on this optimization problem where we're going to be showing that the optimal solution to the function x transpose x, subject to the constraint that jx equals w, is given by this function x, which we have in purple. And our hint to achieve this is that we're going to use Lagrange multipliers. Now, if we reach over to our best buddy Wikipedia, we can see that in order to find the maximum or minimum of our function f of x, which in this case is x transpose x, subject to some equality constraint, g of x, which in this case, we're going to reformulate our jx equals w constraint, and that will be jx minus w equals 0. We use that to form a Lagrangian function, and then we're going to solve for all the partial derivatives, and hopefully that will result in us getting x. So the way we're going to solve this problem is we're going to write down our Lagrangian function L. We're then going to write down our function f of x and our function g of x. Once we have those two functions, we're going to solve for the partial derivative of L with respect to x and the partial derivative of L with respect to our Lagrange multiplier. Using the first partial derivative, we will rearrange that in order to get a preliminary value for x, which we'll substitute into our second partial derivative, which is our partial derivative of L with respect to the Lagrange multiplier, and we'll rearrange that in order to solve for our multiplier. We'll then take that multiplier and we'll substitute it back into our equation for x, and that will give us a solution x with respect to w. And that will hopefully give us our J transpose times J transpose inverse W solution. So I've just moved our problem up to the top here, and in the top right, you can see the result we're aiming towards. And the function L here I've written is our Lagrangian function straight from that Wikipedia page. And we're going to start working towards this. So I'll remove that Wikipedia page now to give us some space. And the first thing we need to do when solving any of these problems is write down our function f and our function g of x. So f of x is going to be straightforward. That's the thing we want to optimize. So in this case, f of x is just going to be x transpose x. And g of x needs to be in the form of g of x is equal to 0. And if we look at our constraint, we don't have that. So we'll move our w over to the left-hand side and rearrange that. So we have my poorly drawn j of x minus w is equal to 0. Now that we have our functions f of x and g of x, and we can rewrite our Lagrangian function and substitute those in, plus lambda j of x minus w. And if we consider our little Wikipedia entry we've taken here, we note that all of the partial derivatives should be 0, including the partial derivative with respect to our Lagrangian multiplier. So let's solve for those now. So our partial derivative of L with respect to x for the first term, this is that one that can be a bit tricky if you've never seen it before. I'll put a link to a pretty nice page that shows you how to solve this in the comments. But the partial derivative, or the derivative of x transpose x, in this case, is 2x transpose. And then the partial derivative of this bit with respect to x is just this first part here, which is lambda j, and no x in the partial derivative there. And now our partial derivative of L with respect to our multiplier is just everything in the brackets here. So that's our jx minus w. And both of these partial derivatives are equal to 0. And this should be enough information for us to solve and get this solution x up in the top right that we're looking for. So I'll get rid of the Wikipedia entry now, and we'll get cracking solving this. So let's start with the partial derivative of L with respect to x, and we'll use that. And we're just going to rearrange that for x. However, before we rearrange it for x, just to make our life simpler, we're going to take the transpose of the whole thing, and because it equals 0, we can do that. Now, 2 is a scalar, so the transpose of 2x transpose is just going to be 2x. And since J is a matrix and lambda we're treating as a vector, when we take the transpose, we need to swap the two of them. So we have J transpose lambda transpose, and that is equal to 0. So now if we want to rearrange this from x, we subtract this J transpose lambda transpose from both sides, and we divide by 2, which gives us x is equal to minus J transpose lambda transpose on 2. And we'll call that equation 1. Now that we have rearranged for x, we're going to substitute this x into our second partial derivative we solved for, which we'll call equation 2. So if we substitute x into equation 2, we get J times x, which we'll put in now as minus J transpose lambda transpose on 2 minus W equals 0. We can rearrange everything now, and we'll add W to both sides. So the minus comes out, and we get J times J transpose lambda T on 2 equals W. And we're going to rearrange this because we're solving for our multiplier. So let's take the 2 across, and in order to move this J times J transpose, we'll need to take the inverse, but we can't take the inverse from the right because we have a vector there, so we'll take it from the left. So one step at a time. Let's move the minus and the 2 across. So we have J times J transpose lambda T is equal to minus 2W. And then we're going to take the inverse from the left on both sides. So if we take J times J transpose inverse here, this just becomes the identity. And we take it from the left here, but because 2 is a scalar, we can put it in between. So what we end up with is lambda transpose is equal to minus 2 J transpose inverse W. And let's call that equation 3. And now that we have a value for our Lagrange multiplier, we can substitute that back into equation 1, and we can rearrange for x. Now, we don't technically need this stuff on the left anymore, so I'm just going to erase that to give us some room. Okay, so working with equation 1, we have x equals minus J transpose on 2, and we substitute in for our lambda transpose. So that is going to be, the minuses will cancel, the 2's will cancel. We have J transpose inverse W. And if we compare with the top right, we can see we've actually already found the x we were looking for, which is the same as J plus W, where J plus is the pseudo inverse, but not really important. So that's the trick for solving this problem. Essentially, take the problem, write down your Lagrangian function, write down your f of x, your g of x, solve for the partial derivative of L with respect to x and with respect to your Lagrange multiplier. In this case, the partial derivative of f of x was the tricky part, which was knowing that that's 2x transpose. Once we have that, we used our first partial derivative with respect to x to rearrange for x. Then we used our second partial derivative with respect to our Lagrange multiplier to solve for that multiplier. And then we substituted that multiplier back into equation 1 to get a form of x with respect to w. And we're done.